All right, everyone. We'll get started for today. So today, Krishna is presenting at a conference, so I'll be covering our lecture 10, which starts brain-machine interfaces and discrete decoding. So before we get started, first, homework 2 is due. So if you haven't already, make sure you turn in homework 2 at the back of class. And then immediately after class, we will upload the solutions for homework 2 so that you guys will have that available for when you prepare for the midterm. Homework 3 will be uploaded to Canvas this afternoon, and it'll be due 2 weeks and 2 days from now. And this will be sort of the first homework where you deal with real neural data and you get to decode and do some cool things that we'll talk about today. Our midterm is in 2 days, this Friday in class. It's in this room, and it'll be 50 minutes during the normal class time from 9:30 to 10:20. The midterm is open notes, open book, and open computer, but it's not open internet. So if you have your notes on your computer, feel free to bring your computer, and you'll be able to use the notes off of that.
So the open computer, can you also use MATLAB if we wanted to?
You could use MATLAB if you want to do a calculation, yes.
Does that mean we can use the internet for access to the network server? Sorry, the license server.
Yes. Although I don't enter, actually I shouldn't say anything. All right. And then Tushar and I still have office hours. So I have my office hours today at 5 to 6 p.m. Tushar will have his office hours tomorrow from 1 to 2 p.m. If you guys have any questions about the material in preparation for the midterm. Any questions on the homeworks, the midterms, anything? All right. So today we're going to start lecture 10, which really gets into discrete decoding. And we're going to first overview what we mean by decoding, but we're also going to start to get into the more mathy part of the class where we get to play with real neural data and real algorithms that translate that neural data into communication or motor signals. And so the required reading assignment for this lecture is this paper by Santhanam, Ryu, and colleagues called A High-Performance Brain-Computer Interface. And in fact, most of this lecture is basically taken from this paper, which was one of Krishna's early papers when he started his lab at Stanford. And then there are 2 other optional readings that you'll find here in case you're curious to learn more about the topic. All right, so as Professor Shenoy talked about in the very beginning of class, we know that neurological injury and disease often result in the permanent loss of motor function. And so oftentimes this can be so debilitating that the person who has the neurological injury or disease can't even feed oneself or communicate. And so for this, we're thinking about diseases like paralysis or ALS. Does everyone here know what ALS is? Yeah. Did anyone dump an bucket of ice on their head in the last 2 years? Yeah, so ALS is, it was great that awareness increased for it through the Ice Bucket Challenge. ALS is one of those is a disease whose causes aren't really well known. But what we know is that it's associated with the death of neurons that control muscles. And so when those neurons begin to die, then you start to lose voluntary muscle control. And that's why it becomes hard to feed yourself or to communicate. A related disease is multiple sclerosis, which was talked about in an earlier lecture. Multiple sclerosis has to do with the demyelination of axons from neurons. And so with those diseases, with multiple sclerosis, what happens is that you can't transmit action potentials over long distances, and it's also slower. And then paralysis, you guys all know, has to do, at least in the cases that we'll talk about, with the severing of the spinal cord. And so while there are surgical and medical interventions that make it possible to sometimes repair nerves in the peripheral nervous system, and so we're thinking about, for example, if you have a finger that's amputated, you can actually, early on, reattach that finger, and you can perform a surgery to have the nerves grow back so that you can restore function of that finger. We actually don't really have any or many effective treatments for the central nervous system. And so we don't know how to treat ALS. Because of this, what we want to do is we want to design electronic medical systems that interface with the nervous system. And these are neural prostheses or brain-machine interfaces. And we're hopeful, and we've begun to see how these brain-machine interfaces or neural prostheses can start to fill some of these treatment gaps. The ultimate goal of any neural prosthesis is of course, to restore normal functionality. And so we hope that, for example, for someone who's paralyzed, that they would ultimately maybe be able to walk again, be able to move their arms as they naturally would, or maybe not their arms, but a prosthetic arm. And then a final note, Krishna had just gone over lecture 9, where he talked about different measurement modalities. And so we've always been talking about measuring action potentials. And if you guys recall from lecture 9, this involves actually doing a brain surgery where we open up the skull and we get access to the brain, and we start to stick electrodes, or these little electrode arrays that Krishna showed with the 10 by 10 grid of electrodes into the brain, and that's really invasive. There are less invasive alternatives. So one of them is EEG, where, and some of you guys might have seen this, you wear actual electrode pads on the surface of your scalp. And these will also record neural-related signals. And then there's a technology called ECOG, which still requires a brain surgery, but the electrodes don't penetrate the brain. So ECOG are these electrode pads that just sit on top of the brain. And what you're measuring there is the average activity of millions to tens of millions to hundreds of millions of neurons. And these less invasive measurement techniques can be used to control a neural prosthesis. And they have the benefit that they're less invasive, or for EEG, completely non-invasive. But the problem, or what the literature is sort of pointing to, is that these recording modalities, EEG and ECOG, may not be high performance enough. So it would be great if you could just put an electrode or put a pad on your scalp and restore normal arm function. But the best that we've been able to see is that if you record from many different pads on your scalp, you can use this EEG system to control 1 bit per second. And so there's actually this cool paper 2 years ago or 1 year ago where they had people controlling quadcopters. But it was very simple in that you just say quadcopter go left or go right or go up or go down. And those are very low information rate systems. That's 1 bit per second. The bit is left or right or up or down. Whereas for controlling the natural arm, we have 22 degrees of freedom in our arm. We make very precise movements. And if we can only transmit information at 1 bit per second, we can't hope to ever gain natural arm function. And so that's why for the rest of this class, we're really going to rely on looking at intracortical prostheses that measure action potentials. No surprise, we've talked about action potentials at length. And that's because we believe that to get to normal function, you will likely have to really record from the action potentials. What's happening? All right, so this is a block diagram that we'll use for the rest of class. So this is your basic brain-machine interface, or motor prosthesis, or neural prosthesis. And what we have here is a brain. This is actually a monkey brain, not a human brain. But you can see that there are many different areas of the brain, and we'll dive a bit more into what these different areas are. But what we'll primarily care about is recording from primary motor cortex, that's M1, and a related area called dorsal premotor cortex. And so premotor cortex sort of sends projections to M1, and premotor cortex is implicated in planning. And some people also record from this parietal region of cortex, and we'll also discuss why that might be. So what we'll do is we'll stick our electrode arrays that Professor Shenoy talked about from last lecture into these areas of the brain. And from there, we'll get our raw voltage neural signals. We'll high-pass filter them and set a threshold so that we can record action potentials. And we might apply one of our spike sorting algorithms, for example, the one that is based on PCA that Professor Shenoy mentioned, to detect the different neurons on each electrode. And so you can imagine this is just for one electrode, but we have 100 of these. And so if I plot a spike raster here, where each row is a different neuron, then we can see across many different neurons we'll have the spiking activity, and we'll know their spike times, and we know that the information is coded in the firing rate of these action potentials. Then, really, all the magic happens here. There's this box called estimate desired movement that translates the spiking activity into either a communication prosthesis where, for example, we would want to interface with a computer. So we would want to use our neural signals to control a computer mouse or to control or to select keys on a keyboard. Or we could use our spiking signals to control a motor prosthesis. And so this is a really state-of-the-art drawing of a robotic arm. So we would connect a robotic arm, and we would have the robotic arm's position or maybe its joint angles controlled by the spike times or the firing rates of our action potentials. And then finally, the system is a bit more complicated than the normal system because this is supposed to be an illustration of an eye. There's an eye which sees the prosthesis in action. So if you're controlling a robotic arm and you want it to go to the right, but your decoder is imperfect and it goes to the upright, then the decoder has made a mistake. And you'll want to compensate for that by now saying, OK, I want to go right. It went upright, so now go down right. And so basically what happens is in this whole system, the human controlling this prosthesis or the monkey controlling this prosthesis closes a feedback loop. Right? And so this is now inherently a closed loop system because the monkey or the human can see the performance of this prosthesis. And if it's doing poorly, the monkey can adjust for it. But then this is also a bit more complicated because if you take an E105, we know that if you put some objects that we know really well in a feedback loop, like a multiplier, a gain term, et cetera, we can characterize those really well. And we can write, for example, the loop gain. But now the feedback loop is closed by a monkey or a human. And that is not something that we know how to model well at this point. And so really, for the rest of the next few lectures, we'll be talking about this box, estimate desired movements. And this is really the topic of machine learning. Yeah, Brian.
Well, can you even say that it is closed loop? Because the human or the monkey has varying response, right? So while you're applying a stimulus set of X, let's say, into the beginning of your plant, or sorry, beginning of your controller, sorry. If the learning is essentially not quantifiable, how can we say it's closed loop?
So when we say closed loop, all we mean is that there is feedback, and that feedback results in a differing command. That loop could be closed in different ways depending on the subject. And then there are also interesting things with learning. So we'll talk about this more when we get to controlling computer cursors. But you could give the monkey a decoder that is not exactly random, but pseudo-random with random weights. And so it might be like the monkey, to move the cursor to the right, has to command something to the left. And so he realizes that, oh, if I think about going to the left, the cursor will go to the right. And the monkey can learn these things. And so in a way, there's also a benefit of having the monkey or the human in the closed loop because they have learning capabilities which exceed a constant gain that we can apply. And so it could be also a good thing that we have the monkey or a human closing the loop. All right. If you've taken machine learning before, and we don't expect that any of you have, if you're curious, this is a supervised learning problem. And so this is something where we have both the inputs, the firing rates of the action potentials, and we know the outputs. We know for some given set of action potentials that the monkey wants to select the letter S, or the monkey or human wanted to move this robotic arm like that. And so because we know the inputs and the outputs, what we want to do is we want to learn a mapping that maps the inputs to the outputs. And so that's this whole block here. All right, so there were two types of prostheses shown here: communication prostheses and motor prostheses. And this lecture will focus on communication prostheses, and the next lectures will focus on motor prostheses. But really quickly, what we mean to clarify the difference between these two are that communication prostheses don't aim to restore natural movements. And so if you want to type, it would be great if you were, for example, paralyzed, if you could regain function of your hand. And so we're thinking like Luke Skywalker's hand at the end of Empire Strikes Back, right? He can like feel exactly what's going on in each finger, and he can control each finger precisely. But if you're a human who doesn't have control of their hands, getting that control of the fingers would be great, but actually typing precisely would be difficult, right? We type pretty fast, so you would have to have the timing down between the fingers correct. Each finger would have to hit the correct key, and you can imagine how this would be a very difficult decoding problem. Instead, an easier way would be just to say, I intend to hit the letter H, so type H for me. And so all of a sudden, instead of trying to command your fingers to type, you're just thinking THE space BROWN, etc. And the decoder is just saying, OK, I know that he wants to communicate the letter T, the letter H. And this is a far easier problem than actually natural typing. And the important thing is that this leads to something that could be very higher performance than if you were to use an imperfect prosthesis that's trying to control your natural fingers. And so these communication prostheses, they really aim to provide fast and accurate communication. So this could be moving a computer cursor on an on-screen keyboard to write out a text message or write out a GChat message, or it could be to select icons on a computer screen or to select an app on a tablet. Because these systems are operating in a fundamentally different way, instead of tapping the Gmail app on your tablet, you're just saying, or you're saying, I want to select this icon, this performance might even surpass the rate at which people can type or speak. We aren't at that stage yet, but it's a potential for this type of prosthesis. Even though we're not restoring natural movements, this could be really helpful for people with ALS or paralysis who are locked in and are otherwise unable to converse with the outside world. And so we think of people like Stephen Hawking. Stephen Hawking currently uses a system that isn't a neural prosthesis, but is essentially a communication prosthesis that relies on both eye movements and muscle movements. And so with these, he's able to, at a pretty slow rate, although better than nothing, of course, type out a message to a caretaker or write a scientific paper. And so being able to reliably type several words per minute on a computer would be a really meaningful advance for these patients, as I'm sure you guys can all imagine. On the other hand, we have motor prosthesis. And so motor prostheses are the prostheses that are involved in actually replicating a natural movement. And so for a communication prosthesis, our goal is to type THE, and we can measure how well we did. If it types, for example, TJE, J is next to H, then we know exactly where the error was. For a motor prosthesis, what we care about is moving an actual robotic arm. And there's a desired trajectory. And so if we want to do this, but it does this a bit, or it slightly deviates off course, there's an error in that trajectory. And this error is more related to like an analog error. What is the error between trajectories, rather than what is the letter that I wanted to type and what's the letter that I did type. And so these motor prostheses are effectively controlling analog variables, right? The continuous movement of your arm through space, whereas these communication prostheses are really caring about discrete selections. And so again, we'll get to motor prostheses starting handout 11, lecture 11, right after this one. With the communication prosthesis, ultimately, the goal is to maximize information throughput, or the information rate. So when you guys download a file from the internet, you guys see values like 1 megabyte per second. And so that megabyte per second is an information rate. You're transferring 1 megabyte in a second. For communication prostheses, we're going to be using the exact same types of measures, except they're going to be many orders of magnitude less. And so we're going to be talking about transmitting 4 bits per second. But it turns out that if you can transmit information at 4 bits per second, it's equivalent to being able to type around 8 to 10 words per minute. And so even though 4 bits per second sounds pretty slow, it could actually be really meaningful. All right. Any questions before we go on? All right. All right, so there are two types of neural activity that we can that we can decode. The first is plan activity. So plan activity is something that you guys are all familiar with. If I want to swat a fly, right? If I just start hacking my arm at it without planning where it's going to be, or if I'm reaching for a cup and I don't plan for how my arm should slow down when I reach towards that cup, then I'm going to do a poor job. So planning is just is the activity where we desire to execute some reach with some precision, with some speed, with some distance, with some direction. And because you guys can form plans, you know those plans reside somewhere in the brain. And it turns out that these plans reside in regions of cortex called the parietal reach region. So this is part of parietal cortex. We won't talk about the parietal cortex that much, but there was a recent paper in the last year where a human implanted with electrode arrays was able to control a prosthesis, and they recorded neurons from parietal cortex. Premotor cortex has a lot of this planning activity. And so when you want to plan a reach, you'll see neurons in premotor cortex start to fire a lot. And then in primary motor cortex is the part of the brain that actually sends axons down the spinal cord and it actually hits your muscles. Primary cortex has more true movement activity, but there is some plan activity in primary motor cortex. And so you make a plan to hit a target, and then you actually, for example, or to swat a fly, then you'll actually have the movement where you go and swat a fly. And so this movement is the activity that actually goes down your spinal cord and eventually communicates to your muscles to contract them so that you can make a desired movement. And this activity is present 100 to 200 milliseconds in your motor cortex before and during the movement. Can anyone tell me why that is? Feedback has an aspect to do with it. I'll address that after, or I'll address that after the main answer to this question. But the main answer is that we know that there's a time constant, right, to transmit action potentials through the nervous system, because we know that there's the axial resistance and there's the capacitance as well. And so transmitting action potentials, we know, takes time. And so it turns out that this 100 to 200 milliseconds is the latency it takes for an action potential to go from your motor cortex down your spinal cord and then eventually hit your muscles. And so it seems pretty slow, but it's fast enough for us to interact with the world. And then what you're saying about feedback, there's a similar latency. So if I am looking at the screen, the photons from the screen will hit my retina. Then that'll go through the optic nerve into my visual cortex. And that will also be about 100 milliseconds. And so there is a delay from the feedback also. Yes?
Last lecture, Dr. Shinoy mentioned that the latency on the computer end, or like the spike sorting and all of that kind of processing, could be up to 50 milliseconds. Is that because that's still significantly less than this range, or is that gotten anything else?
Yeah, so all the processing that we do on our computers, so to rephrase this question, if I wanted to spike sort on my computer, but sorting spikes took 300 milliseconds, then that would be really bad, right? Because as soon as I sorted the spikes and I had them available for use, there's a large delay. So imagine, let's make it 1 second. Let's imagine that I made a command, but the decoder took a second to process all the neural signals and then respond. That would be a horrible decoder to use because it's going this way, and you want to say, oh no, I want to go this way. But you have to wait a second for that command to actually start to affect the decoder. And so you have this long loop time, and that could be really frustrating to use. And so you're correct that all the processing that we do is slower than this latency. And really what we want to do is we want to make that latency as close to or as small as possible. So on the order, maybe even less than 10 milliseconds. And that's actually what we have in the lab these days.
So,
Yeah.
this is sort of jive with sort of real life.
Yeah.
Is there some parallelism going? If you're playing ping pong
Yeah.
or video gaming,
Yeah.
your reaction time is faster than
Yeah.
0.2. So
How does that happen?
Yeah.
Yeah, so there's also really incredible machinery in the brain that implements things called forward models. And so if all you saw was the ping pong ball coming at you, and then you had your 100 millisecond latency to get to your visual cortex sends it to motor cortex sends another 100 millisecond command down to the arm, we couldn't play ping pong. So what happens is that you have a forward model in your brain where you are basically inferring where the ball is going, right? You have that model of how the ping pong ball moves. And because of that, your brain is able to perform these computations to say, OK, I'm pretty sure the ping pong ball is going to end up right here. So when the ping pong ball is here, or the tennis ball, I'm already going to start my swing so that when it gets there, I'll hit it.
there's also a very local process if you touch your finger on a hot kettle.
Exactly.
So it doesn't have to go right the way through.
Yes, yes. So there are also local spinal cord circuits. And the latency of those circuits is much faster. So the latency of those circuits, I believe, is about 50 to 70 milliseconds. You don't have to know this for the class. But in case you're just interested, those circuits operate much faster because they don't have to go through the cortex. All right, so movement activity is also tuned, or it encodes direction and the speed of your arm. And movement activity is primarily found in primary motor cortex. It's also coded in dorsal premotor cortex, although it's more so in primary motor cortex M1. And then there's some encoding of movement activity in the parietal reach regions. All right, so we're going to show you a video now where we have data sets from monkeys with both plan and reaching activity. And so in this video, you're going to see both a plan and a reach. And so the monkey holds a center target, a peripheral one appears, and the monkey reaches to it. Can I pause this? I cannot pause it. OK. So what I want you guys to watch in the video is when the target appears, the monkey isn't going to reach immediately. The target is going to be small, and then it's going to grow big. When it grows big, that's the monkey's cue to reach. And so there's going to be a planning period. It's just a few hundreds of milliseconds where he's still holding the target, even though the target that he wants to reach to has appeared. When his center target disappears, then he'll be able to actually perform the movement to that target. And so hopefully you'll see that more clearly here. So he's holding, target appears, he plans, and then reaches. Plan, reach. So it's a bit hard to, oh yes, Gary?
Just wondering, how do you differentiate between planning activity versus like sensory activity, or is that the same thing in this case?
Yeah, that's a good question that is difficult to answer. We record activity in the premotor cortex, and we think that it has to do with the plan, the monkey's intent to make a reach. But that activity is also modulated by, for example, if I took this target and then I jumped it, there's the visual change that the target jumped from here to here. And so both the monkey's plan will change from reaching from this target to this target, and this incoming sensory information will change because visually you saw the target change. And it's really difficult for us to disambiguate between the two. And so for intents and purposes, you can consider that's also part of plan activity in this class. Although we would think that that activity, the sensory information, is transformed in earlier parts of cortices. So in the visual cortex, it's transformed. And it passes through, for example, parietal cortex to eventually reach your motor cortex. And hopefully, we think that when it gets to your motor cortex, it isn't just the pure sensory information, but it's related to how you should process that sensory. This lecture, which we'll finish on Monday, you guys will actually see what this box is for this box. In this lecture, it'll be something called a naive Bayes decoder. And that interpret neural signals box will say, OK, I saw these firing rates, and I'm going to predict that the monkey wanted to reach up and to the left. And so that's exactly what we want. All right. And so again, just at a high level, to show you the flow before we actually get into showing you a video of the decode and how we fit the decoder, we have a monkey. He is holding a center target. Oh, whoops. And then a target appears up and to the left. We've implanted our electrode arrays. Those electrode arrays are giving us the raw voltages on 100 different electrodes, or 96. 4 of them are ground. That's why we say 96. From this, we high-pass filter the signal to remove this slow, low-frequency potential, so we can draw a threshold to reliably detect the spikes. That threshold will give us multiple spikes on each electrode. And from there on out, we'll spike sort these different spikes. Then we're going to build the tuning curves, the heat maps that I just showed you. That's basically a tuning curve. We'll build a tuning curve for each of these neurons. And then across all the neurons that we have, we're going to be able to measure their firing rates. We're going to pass it to our decoder. We're going to decode then which target the monkey had planned to reach to. And then we're going to send that signal to the screen, and we're going to draw a circle around the target that he intended to reach. And so the circle denotes the intended target. And there are a bunch of studies that have used this approach, and they're here if you're curious of looking for further. And Krishna writes here, if there's magic, here it is. And so just looking at this, it might be difficult to actually see by eye what target he wants to reach to. In fact, I can't do it. But our decoders will be smart enough to handle this. And so we're going to show you a video now of this decoder in action. And so what you're going to see is the monkey is going to be performing a similar task to before. He's going to hold a center target, and a target is going to appear at one of the 7 locations. And then the monkey is going to plan to reach that target. And then we're going to decode that plan activity. And where we decode, we're going to draw a circle. And so if you see a circle appear around that target, it indicates that we decoded that target correctly. And then we're also going to interleave real reaches here just to keep the monkey reaching every once in a while. So that's a decode. We're going to reach, a reach, decode, decode, decode. Was that all clear to everyone? Nathan?
Are these directions, are you able to measure a magnitude?
We are able to measure magnitude as well from the plan activity. So the plan activity also has information about the speed and the distance of the reach that you're going to make. And so these targets, actually they may not have been equally spaced, but you can imagine a circle of targets at say 4 centimeters away, and then another circle of targets at say 8 centimeters away. And this is really good. We'll talk about this more in the next class, because if you have more targets, you can convey more information, right? If I have just 2 targets, I can only convey 1 bit. One target is a 0, and the other target is a 1. And if I have 4 targets, then I can convey 2 bits of information, right? One target is 0, 0, 0, 1, 1, 0, 1, 1. So the more targets, the more information I can convey per selection. But then what's the problem of putting up too many targets? Yeah, it's harder to, so if I put up more targets, then all of a sudden my accuracy is going to go down. Because now to differentiate between the target, say at 4 centimeters and the target at 8 centimeters, if this neuron cares more about direction rather than distance, then they might be hard to disambiguate. And so there's a trade-off there, and we'll talk about that. Yes?
So if he's supposed to plan but not reach,
Mm-hmm.
and if he chooses, like on these which are the ones with the circles, and if he chooses to reach, won't he still get his juice?
So the task is very specifically designed such that if he reaches while this target, so for the BMI, for the neural decode trials, this center target was always there, and that's his cue that he's not supposed to reach. And so if he reaches while the center target is illuminated, the trial automatically fails and he doesn't get juice. So monkey training is something that is very much an art and it takes a long time. If you have really well-trained monkeys, you can get a lot of really good data. And so training all these very specific things, there's a plus here. The monkey has to watch that plus with his eyes. And if the monkey's eyes move a bit, so if he looks at the target, the trial fails. And we're doing this so that it's not necessarily, we're not decoding the eye movements to the target. We're only decoding his motor actions, his arm actions. And so there are all these very precise controls. And just to give you a sense of it, there are some tasks that we run in the lab that literally took a year to train the monkey to do. And so monkey experiments are very time-consuming, but they afford this really unique opportunity to get really cool data. All right, so I'll leave off here actually because this is basically starting the parameter selection part of our discrete decoding. Are there any other questions about homework, midterm, this lecture? We have a minute, but if not, then you guys are welcome to take off. All right. Tushar, are they great? Do we enter the grades into Canvas? You haven't? OK.
On the last video,
yeah.
when it was said like the